All right, so welcome back. We are going to continue our discussion on math used in the physics classroom. So today our objective is to use metric prefixes appropriately to express physical values, and then to convert from one unit to an equivalent amount in a different unit, and then to recognize how to use units to check your work. There are some approximations you should be familiar with in the metric system. So again, these are on your reference table here. There we go. That's better. Now they're not backwards. Okay, so here, the prefixes to the power of 10, the lower left-hand corner of your reference table. You can look at them there. You can see it there. So 1 meter is about 1 yard. It's the tip of your nose to a fingertip away, or one long step. 1 centimeter is about a pinky nail, sorry. Then you have 1 millimeter, which is about the thickness of a fingernail. Then 1 kilogram is about 2.2 pounds, or approximately the mass of a pineapple. I also think about it because I used to live in Japan for a couple of years, and I had to go to the store, and on the meat package, it would say that I was getting 500 grams of meat, and I knew that my recipe was 1 pound, so I knew that 500 grams was 1 pound. So that's approximately how I would convert in my head, and still how I think about it. Anyway, approximations are good because they tell you if you are on the right track with your answers, and it allows you to have an appreciation for the numbers. We're going to work with this a little bit next week, so you have a better idea of why approximations are good, but this is where we're going with that. And it does come up on the regions. Okay, so here's an appreciation for the numbers in real life. This is Mr. Medina. He works at Ward Melville. He was my teaching teacher, so he taught me some things about being a physics teacher. Anyway, he found this sign over by the MacArthur Airport, and it says that 1 kilometer is about 1 mile, which is just not true. 1 kilometer is about half a mile, which is a huge difference. So anyway, it's just something that we need to keep in mind so that we can be global citizens and make sure that we are we don't look silly, for one thing, in front of the rest of the world. So anyway, there's something we have to consider when we're doing labs and physical things, measurements, and that's errors. All physical measurements are subject to error. Some come from the method that's used, some from like the environment. Maybe the fan was on and it was changing something about the experiment. Sometimes it's an instrumental limitation, or sometimes you did something wrong, and that's okay because we're scientists and sometimes we do things wrong, but we learn from them. Systematic errors, though, are in one direction only. It's something that happened once and then it builds upon itself. But random errors, it happens in all kinds of different directions. And it might be reduced if you repeat the number of trials that you do. That's why we repeat them. Okay, so then we have something called precision. And there is a difference between precision and accuracy, but I'm only going to talk about precision right now. It is the degree of exactness of a measurement, and it is determined by the instrument used. So for example, if you have a handheld instrument, the precision is half of the smallest mark, which is estimated. So a handheld instrument might be a ruler, and the smallest unit on this ruler is a millimeter, but the numbers are in centimeters, so 1 centimeter is 10 millimeters. But the precision of the ruler is half of that millimeter, so you can estimate in between the millimeter marks, and that is where your decimal place must end. Okay, significant figures are those known to be reasonably reliable. Therefore, all measured figures and one estimated figure would be considered significant. For example, if you divide 52 divided by 2.3, you get this really long number, 22.608,695,652,173,9. That right there is the millionths, that one's the billionths, and that one's the trillionths, and that one is the quadrillionths place. But there's no way you can vouch for the measurement to the quadrillionths place. So don't even try. And last year, I'm sure you really studied and focused on significant figures. We don't do that in physics so much. So if you just make sure to keep 2 to 3 significant figures, you'll be fine for the year. Unless we tell you otherwise. It doesn't come up often, but sometimes it does. But for the most part, 2 to 3 significant figures, and that's where you need to be. Okay. So for the next little thing, there are some things that come up, even just in the prefixes to the power of 10 on your reference table. There are some, there's like one, I think, letter that's a little weird. It's this mu. Where is it? Right here. This is a Greek letter, and we actually talk about some of the other Greek letters as well. You're familiar with pi, I'm sure. So that's something to keep in mind. Theta is a Greek letter. That's where they come from. It's the Greek alphabet, and they'll come up. That's where you need to look if you're confused about what the new symbols are. They just represent things. It's not a huge thing. Anyway, so for conversions, in order to convert something into an equivalent amount in a different unit, you will need to multiply by fractions which equal to 1 and cancel out like units. So, let me get this. Okay, so if you want to take the mass of a crate of eggs in kilograms, you want to find it, you know that one egg is about 57 grams. One crate is equal to 432 cartons of a dozen eggs. So convert the mass of the crate of eggs in kilograms. So one crate, I'm just going to say 1C because I will run out of room, is going to be, so we're looking for the mass of one crate. So we start with one crate. And then in one crate, that's equal to 432 cartons of a dozen eggs. So carts of 12. So in one cart of 12, there are 12 eggs. So like that. And then we can further go on so that it is then one egg is equal to 57 grams. Okay. And then if you put that all into your calculator, you will get a number. And I don't actually have a calculator right now, but I can pull it up here. So then we have, it comes up, 432 times 12 times 57 grams. So it's asking for it in kilograms. So so then we have to divide by 1,000. So it's 295 kilograms for one crate of eggs. So that's what this equals to. So I will show you this in many different ways as we go on. This is just a quick example. So if you look, the 432 cartons of 12 divided by one carton, that's just dividing by one. It's just a fancy way to divide by one. You may have seen this in chemistry, I'm not sure. Okay. So then dealing with units, by making sure you end with the right units, you will catch a lot of wrong answers. So here we have an equation. It says D equals VT plus 1/2 AT squared. And then it asks for what the distance is if the distance traveled is if the V is 10 meters per second, the T is 7 seconds, and the A is 6 meters per second squared. So you can actually plug these in, and it would be 10, oops, it would be, I'm going to go back. So here we go. So it's 10 times 7. And then we say plus 1/2 times 6 times 7 squared. So if you remember your PEMDAS, it's going to be parentheses first. This looks like there's a lot of parentheses, but not really. And then exponents. So the exponents is 7 squared. So 7 times 7 is 49. And then 49 times 6. And then divided by 2 to make it a half is 147. And then we have to do 147 plus 10 times 7. 10 times 7 is 70. So we can say 147 plus 70. And that's 217. Okay, so now we have the number. That's cool. 217. But that doesn't really mean anything. 217 what? So if we go through and do the exact, the VT is meters per second, and it is times a second because it's times time, right? So V is meters per second, the T is times seconds. So this and this go away and it's just meters, all right? So we have meters here. That's cool. That's what we're looking at because we're looking at a distance. Distance is supposed to be in meters. Then we have 1/2. That's just a number. We can convert that to 0.5 if it's easier for you. And then we have an acceleration. That's what that A is. And that is meters per second squared. And then we multiply it by T squared. So the T squared is in seconds, so it's going to be seconds squared. So then the seconds go away because they cancel out. Whoops. They cancel out because it's seconds divided by seconds there. So then we end up with meter plus meter, ignoring all the numbers. And then that's still in meters, so that's still a distance. And that means that our 217, that we're on the right track. We did our math at least somewhat correctly because we treated the units the same way we treated the numbers, and we got to something we expected. So that's good. So I have just a little bit of a you try now. As soon as I delete. Anyway, the next one is for you to try, and it's VF squared equals VI squared plus 2AD. See if you can figure out the answer, and I will leave that as a Google form quiz for you at the end. You have the VI goes here, is 20 meters per second, and then 2 times A, which is the 12 meters per second squared, and then times D equals 31 meters. So you have to put these together, and then these together, and then add what you get here. And then that's VF squared. You can just solve for the VF squared. You don't have to find just the VF by itself. But as a challenge question, consider what you might do if you need to solve for VF by itself. All right. Thank you, and I will see you next time.